Welcome to this lecture on data structures. In this lecture, we will try to quickly see if we can optimize the queue implementation using arrays. In our previous lecture, when we were trying to analyze different implementations of list, stack, and queue using arrays, linked lists, and a different version of linked list with a tail, we found that we were able to optimize all of stack's operations. But when it comes to the queue operations using arrays, we said that we could not optimize both insert and delete at the same time because queue is a FIFO structure and we had to insert and delete at opposite ends. And because the list operations insert and delete from the start of the list are not optimal, both of them take order of n, we said that either insert or delete, one of these two would take the hit in terms of the runtimes. So if you're trying to insert from the start, insert would be not optimal, it will be order of n. But if you're deleting from the start, delete would be not optimal. Whereas delete and insert at the end of the list were optimal at their order of 1 because they would not involve any shifting of value. In this lecture, let's try to see optimize the implementation of queues using arrays. It turns out that the inserts and deletes of queues are optimized by a special kind of a queue called as a circular queue. A circular queue is something that doesn't use list abstract data type to implement the queues operations of insert and delete. We have to maintain our own array as the data structure and perform operations on the array, and we have to move away from having to use the list abstract data type implementations. So this doesn't use the list ADT implementation, but instead maintains its own array along with special indexes. And those special indexes are called front, using which we delete elements from the array, and there is another index called as rear, using which we insert elements into the array. Let's try to take an example and illustrate how this circular queue works. So let's take an example of an array which has 10 elements in it. And as we said, the circular queue has two indexes. The first one is the rear, using which we insert elements, and the second one is the front, using which we delete the elements. So initially, both front and rear are initialized to -1. So front is -1 and rear is -1 as well. So when front and rear are both -1, the array doesn't have any elements. So this is one of the conditions for the queue to be empty. So let's jot down the emptiness condition here. So queue is empty when rear equals to front equals to -1. So this is one of the conditions which indicate that the queue is empty. Now let's start trying to insert elements into the queue. So let's say we inserted 1. When the first element is inserted, we point the rear to the 0th index. Along with it, we also point the front to the 0th index to indicate that the first element has been inserted. So front also points to the 0th index. So the fact that front and rear both point to the same index indicates that there is one element present in the queue. So let's keep the front as it is and then try to see what happens when we have inserts happening into the queue. So let's say we have 2 inserted into the queue. Rear moves one element, one index to the right. Say we have 3 being inserted next. Rear moves another position to the right, another index to the right, and so on. So the increment, so let's talk about the insert implementation. So what we do is we move rear to the right by 1 index, and we assign the value to be inserted into the array using the rear index. This is a very simple enough operation. So this goes on till the point where rear reaches the end of the array. So let's say we inserted 4, 5, 6, 7, 8, 9, 10, and rear has reached the end of the array. So at this point, you cannot insert any more elements. So there is a condition that we need to check to discover that the array is full and no more elements can be inserted, which has to be done as part of your insert. And the condition for fullness is that rear equals to size of array -1 and front equals to 0. Okay, so the fullness condition for the array or the queue requires both rear and front to be wide enough to occupy the whole array. And let's take a scenario where before the rear index reaches the end of the array, you had performed a few deletes as well. So let's assume that 1 is deleted. So what happens is you would, let's try to jot down delete as well. So first thing you do is you save the value to be deleted into a temporary variable called value, and you use your current front index to assign the value, and you then increment your front. So your front now moves one place to the right. So now your active queue would be from this point to this point, and this point is kind of not existing as far as your logical structure of the queue is concerned. So this goes on. Say for example we delete 2 and 3 both. So your front now points to the index 3. Now at this point your rear, even though it points to the end of the array, does not signify a queue being full, because you still have spaces here that were emptied out by your deletions because your front moved ahead, deleting some of the elements that were inserted before. So what you can do is you can actually circle back your rear to the front of the array, and that condition is achieved by rear plus 1 percentile size. So in this case your rear is 9, plus 1 is 10, and percentile 10 is 0, which would circle back your rear back to the 0 things to insert any new element. So let's say we have inserted a new element to the queue, say 11, and your rear points now to the 0th. So we modified this condition to make sure that your array now becomes a circular array, or your queue becomes a circular queue, so that your indexes that fall off the range of the array circle back to take advantage of the empty spots that are created by deleting elements in the interim. So let's say this continues and you have inserted 2 more elements. So your rear moves from 0 to index 2, at which point now the queue is full again. So the fullness of the queue can be discovered from the condition that rear equals to size minus 1 and front equals to 0, which is when the front is at 0th index and you have rear just about to fall off of the range of the array, or as we just discovered in the case where rear equals to front minus 1, where rear has circled back to the start of the array and then follows the front, but front cannot delete enough elements to go wide enough for the array to be empty. So you have rear catching up front and not having enough spaces between rear and front for new elements to sit. So these 2 conditions are where you check the fullness of the queue. So insert works this way. So you increment the rear to point to the next empty slot. Before doing that, you basically check for the fullness condition, if rear and front span the whole array, or if rear is just behind front, you don't have any empty spaces to insert your elements, so you reject the insert. Otherwise you increment your rear, but again make sure that you fall off the cliff of the array and then circle back to the start of the array before you insert the element into the array. Now let's try to understand how delete works. What is the emptiness condition? So emptiness condition was rear and front both pointing to minus 1. So let's try and see what happens if you delete all the elements. So I'm now deleting 4, 5, 6, 7, 8, 9, 10. So my front would, so just before deleting 10, my front would point to the 9th index. And obviously to make sure that the front also circles back to the start of the array, you would have to do a modulo operation when you're incrementing front. So in this case, again, it's 9 plus 1 modulo the size of the array is 10, so it will be 10 percentile 10, which is 0. So your front would circle back to the start of the array. So moving on, so when I delete 10 as well, my front would point to the 0th index. I delete 11, 12, when my front would point to the index 2. So this condition is where my rear and front have the same value, same index value. So this is where I just have one element. So when you're trying to delete the last element, what you have to do is to check if your front is equal to your rear, which means this is the last element which you're trying to delete, in which case the queue would then become empty, which means you would go back to the state where your rear equals to minus 1 and front equals to minus 1. So in this case, when you're trying to delete 13, you just delete 13, push back rear and front to this condition. So this is a condition where queue is empty. So by having this tweak piece of logic in your delete operation and making sure that this condition is sufficient to make sure that you discover when the queue becomes empty. And yeah, so that's pretty much it. So delete basically saves the value before it increments the front pointer or front index by making sure it circles back to the start of the array if it falls off the cliff of the array. And before even we do that, we check if the front and rear are equal, in which case we set the rear and front to point to minus 1, a values of minus 1, so we can discover an empty queue when one tries to delete. So you have your emptiness check being performed here. Here you're performing your fullness check in insert even before you go ahead and perform your rare arithmetic and insert in the array. That's pretty much it. So both the operations insert and delete are order of one, because all we are doing is to manipulate the values of the front in delete and rare in insert, and just assigning the value at a particular index in insert and saving value at a particular index in delete before doing the manipulation and returning the element as the value from the delete function. And both of these operations are order of one. And one thing to remember is that even though we're showing this illustration by rubbing off the elements inside the array, it doesn't matter if the elements exist in the array or not. All we are concerned about logically is the range between the front and the rear. So again, depending on whether your rear has circled back or not, your range can change, but then you're not concerned with any value that is outside the range that's spanned by your rear and front. So if you can logically think your circular queue to be a circle like this with your 0th index and the last index joined together, your array's span by the front and the rear is your queue, and everything else outside this range or span is not part of the queue. Even though there are valid elements in it, you don't care about them. So for instance, if you take your front to be here and your rear to be somewhere here, your array is only this, your list, your queue is only this part, while the rest of the array might contain values which we don't care. Okay, so this was circular queue, which optimizes the array implementation of queue to perform the operations in order of one time. And the only tricky part is to make sure that the edge cases of discovering the fullness, emptiness, and the index arithmetic to ensure that the indices don't fall off of the cliff of the array are the only tricky parts in the circular queue. Otherwise, it's a very simple data structure which gives optimal operations with minimal and simple logic.